Imagine trying to predict the future. It's a tantalizing idea, and in many ways, that's what science aims to do. In the vast universe of data, linear regression emerges as a powerful tool for understanding relationships and making predictions. At its core, linear regression helps us understand how one thing changes in relation to another. Imagine plotting points on a graph where each point represents a piece of data. Linear regression seeks to draw a straight line that best fits these points, revealing the underlying pattern and allowing us to make predictions. Let's consider a simple example. Suppose we want to understand the relationship between the number of hours studied and exam scores. We collect data from several students, recording their study hours and corresponding exam results. By plotting this data and applying linear regression, we might find a straight line that slopes upward, indicating that as study hours increase, exam scores tend to rise as well. This line, representing the linear relationship, allows us to predict the exam score of a student based on their study hours. The beauty of linear regression lies in its simplicity and interpretability. The equation of the line provides valuable insights. The slope of the line quantifies the strength of the relationship. A steeper slope suggests a stronger connection between the variables. The intercept, where the line crosses the y-axis, tells us the expected value of the dependent variable when the independent variable is 0. Whether we're analyzing exam scores, stock prices, or the movement of celestial bodies, linear regression equips us with a powerful tool to decipher patterns, quantify relationships, and make informed predictions about the world around us. It's a fundamental building block in the grand edifice of scientific inquiry. Linear regression shines when it comes to modeling relationships between variables. The heart of this technique lies in its ability to capture how changes in one variable, the independent variable, relate to changes in another, the dependent variable. This relationship is represented by a simple yet profound equation. Y equals mx plus c. In this elegant equation, y represents the dependent variable, the value we want to predict. The independent variable, denoted by x, is the factor that influences y. The coefficient m represents the slope of the line, indicating the strength and direction of the relationship. A positive m suggests a positive correlation. As x increases, y tends to increase as well. Conversely, a negative m implies a negative correlation. Lastly, CE is the y-intercept, the point where the line intersects the y-axis, representing the value of y when x is 0. To grasp the power of this equation, let's imagine we're studying the relationship between advertising spending and sales revenue. We collect data from a company, tracking their advertising expenditures and corresponding sales figures over a specific period. By applying linear regression, we can determine the equation that best fits this data. The resulting equation might look like this. Sales revenue equals 2.5 times advertising spending plus 10,000. This equation tells us that for every dollar spent on advertising, the company can expect a $2.5 increase in sales revenue, in addition to a baseline revenue of $10,000, even with no advertising. Armed with this knowledge, the company can make informed decisions about their advertising budget to optimize sales. Time, that relentless river, carries with it a wealth of data. From stock prices fluctuating like waves on the market sea to temperatures rising and falling with the seasons, time series data reveals patterns and trends that shape our world. Linear regression, with its ability to model relationships, extends its reach into the realm of time series analysis, allowing us to forecast the future based on past observations. Imagine we're tasked with predicting the demand for a particular product over the next quarter. We have historical sales data spanning several years, a treasure trove of information waiting to be unlocked. By treating time as an independent variable, we can apply linear regression to identify trends and seasonality in the data. For instance, we might observe a consistent upward trend in sales during the holiday season, indicating increased demand. Linear regression captures this pattern, allowing us to forecast higher sales during the upcoming holiday season based on the historical trend. Moreover, we can incorporate additional variables such as economic indicators or marketing campaigns to enhance the accuracy of our predictions. However, time series data can be complex and often exhibits non-linear patterns. While linear regression provides a valuable starting point, we must be mindful of its limitations. In cases where relationships are non-linear or influenced by factors not captured in our model, more sophisticated techniques might be necessary for accurate forecasting. Linear regression, while a powerful tool, is not a one-size-fits-all solution for every prediction problem. Just as the universe is filled with a diversity of celestial objects, each governed by its own set of laws, the world of data analysis offers a range of predictive models, each with its strengths and limitations. When relationships between variables are non-linear, linear regression may fall short. Imagine trying to fit a straight line to a curved path. The fit would be poor, and our predictions would be inaccurate. In such cases, we must venture beyond linearity and explore other models that can capture the complexities of the data. Polynomial regression, for example, allows us to model curved relationships by introducing higher-order terms. Other models, such as decision trees and neural networks, excel at handling complex nonlinear patterns and interactions between variables. These more sophisticated techniques often require larger datasets and more computational power, but offer greater flexibility and accuracy in modeling intricate relationships. Choosing the right predictive model is like selecting the right tool for the job. While a hammer is perfect for driving nails, it's ill-suited for turning screws. Similarly, understanding the nature of our data and the specific problem we're trying to solve is crucial in determining the most appropriate predictive model. By carefully considering the strengths and limitations of each approach, we can select the best tool for the job and unlock the secrets hidden within the data.